Somewhere in America, right now, a system is watching the ground. It sits in server rooms and on mountain ridges and on the ocean floor. It listens through sensors buried in rock and soil across thousands of square miles of the most seismically active coastline in the Western Hemisphere. It is always on. It never sleeps. And it is supposed to be the thing that stands between you and the worst minutes of your life. The system is real. The technology works. The science behind it is sound. And for the majority of Americans living in earthquake country, when the ground finally moves, the alert will not come. Not because the servers went down, not because the algorithm failed, not because someone forgot to flip a switch. The alert will not come because the system was never designed to reach you. Because the blind spot in America's earthquake warning infrastructure is not a bug someone is working to fix. It is a feature of how the system was built, what it was funded to do, and who it was built to protect. Stay with me, because what the system can see and what it cannot see are two completely different maps, and the gap between those maps is where most of the country lives. If this is the kind of deep, unfiltered coverage, you come here for the kind that goes past the headline and into the ground beneath it. Make sure you are subscribed to Drowsy Space so you never miss a story as it develops. Hit the like button if this matters to you, and drop a comment telling me where you are in the world right now and what time it is as you watch this. And tell me this, you live somewhere in America. Your phone is in your pocket, and somewhere beneath you, a fault system is loading. Does your phone have a system watching for that? And do you actually know the answer to that question? Let me know in the comments. Now let us get into it. Part 1. The system that is supposed to save you. The official name is Shake Alert. It is operated by the United States Geological Survey, the USGS, in partnership with university seismology departments and state emergency management agencies along the West Coast. It went live in California in 2019. Oregon and Washington came online in 2021. And since then, it has issued real alerts for real earthquakes that reached real people's phones in the seconds before the shaking arrived. That is not nothing. That is in fact a remarkable technological achievement. The physics of what Shake Alert does every time it fires is genuinely impressive. An earthquake begins when a fault ruptures, releasing elastic energy stored in rock that has been locked under tectonic stress for years or decades or centuries. That energy radiates outward from the rupture point as seismic waves. The first type to arrive, the P wave, or primary wave, moves through rock at roughly 6 kilometers per second. It is fast, but it is also weak. It arrives before the shaking you feel, before the damage begins, before the moment of crisis. And Shake Alert's job is to detect that P wave, calculate the earthquake's magnitude and location in real time, and send an alert to every phone in the projected shaking zone before the second type of wave, the S wave, arrives. S waves are what shake buildings. S waves are what knock people off their feet and topple structures and send objects flying off shelves. They travel slower than P waves, roughly 3.5 kilometers per second. That difference in travel speed is the window Shake Alert is designed to exploit. Detect the P wave, calculate the threat, send the alert, all before the S wave arrives. On paper, this system gives you time. Seconds maybe. A minute or two if you are far enough from the epicenter. But time. Documented, real, potentially life-saving seconds in which a surgeon can pull a scalpel back from a patient's body. A train operator can apply brakes before reaching a damaged section of track. A child can duck under a desk. An elevator can stop at the nearest floor and open its doors. That is the system. That is what it does when it works. When the ground starts moving, how many seconds do you have? And does the system even know to start counting? That question is the center of everything that follows tonight. Because the answer for most Americans is not what the official press releases suggest. And the gap between what Shake Alert promises and what it can actually deliver is larger, more geographically significant, and more politically uncomfortable than any single agency has been willing to say plainly. Part 2. How Shake Alert actually works. To understand the blind spot, you first have to understand the machinery. And to understand the machinery, you have to understand what the system is actually measuring and how it makes its decisions. Shake Alert is a network of seismometers. physical instruments embedded in the ground at fixed locations across California, Oregon, and Washington. These instruments are sensitive enough to detect ground motion at scales far below what any human body could feel. They are constantly recording. The data streams in real time to processing centers where algorithms analyze the incoming waveforms and make rapid decisions about whether what they are seeing is seismic energy from an earthquake or noise from a passing truck, a nearby construction site, or ocean microseisms, the constant low-level vibration of the sea that seismologists filter out as background. When the system identifies a genuine seismic signal, it begins a rapid sequence. It locates the source. It estimates the magnitude. It calculates the expected shaking intensity at points across the surrounding region using ground motion prediction equations that translate earthquake parameters into expected surface acceleration at distance. And it issues an alert. The entire process, from the first seismic wave arriving at the nearest sensor to an alert reaching your phone, takes between 2 and 8 seconds depending on the proximity of the sensors, the complexity of the event, and the speed of the data transmission chain from seismometer to processing center to government server to wireless carrier to your device. Think of the system like a smoke detector for the ground. A smoke detector samples the air near its sensor. If it detects smoke particles above a threshold, it activates. It does not care about the fire 3 blocks away. It responds to what it can sample locally. Shake Alert works the same way. It responds to what its sensors can sample, and the sensors are only in 3 states. When the ground starts moving, how many seconds do you have? And does the system even know to start counting? For a Californian living near a dense cluster of Shake Alert sensors in the San Francisco Bay Area, the system might detect an earthquake within 2 seconds of rupture initiation and send an alert to their phone within 5 seconds. If the S-waves from that earthquake are still 20 seconds away, that person has 15 seconds of warning. That is real. That is meaningful. That person has 15 seconds to make a decision that might determine whether they spend the next week in a hospital or walk away from the event intact. But the system only works like that if the sensors are close, and the sensors are only in 3 states, which means the system only works at all in 3 states. And in those 3 states, it does not work equally well everywhere. Part 3. The blind zone. Here is the first thing nobody says clearly enough, even in the official USGS documentation, even in the press coverage that surrounded Shake Alert's launch. Every earthquake early warning system in the world has what seismologists call a blind zone. It is not a flaw specific to Shake Alert. It is a physical consequence of the way seismic waves travel through the Earth. And in California, the most seismically active state in the country, the blind zone sits directly beneath the most densely populated urban corridors in the western United States. The blind zone is the area around an earthquake's epicenter, where the early warning alert arrives at the same time as the shaking itself, or after it. Because the alert can only be sent after the seismic waves reach the sensors, and because the sensors cannot be at 0 distance from every possible rupture point, there is always a geographic ring around any earthquake where the warning time is 0. For a major earthquake on the southern San Andreas Fault, the portion of the fault running through Greater Los Angeles, the blind zone encompasses much of the Los Angeles metropolitan area, more than 13 million people, not because the sensors are not there, the sensors are there, but because when the fault ruptures, the shaking reaches the surface so quickly, and the sensors need at least a few seconds of data to make a confident calculation, that the alert and the shaking arrive at roughly the same moment. Think about what that means in practice. The Shake Alert system could detect a magnitude 7.8 rupture on the southern San Andreas and issue an alert within 4 seconds of rupture initiation. But in communities sitting directly above the fault, the S-waves arrive in 3 seconds. The alert comes 1 second after the shaking begins. For those communities, there is no early warning. There is only the earthquake itself. When the ground starts moving, how many seconds do you have? And does the system even know to start counting? The blind zone is not static. It is proportional to the distance from the epicenter. For events close to the surface directly beneath population centers, the blind zone is large. For deep earthquakes, or earthquakes far from populated areas, the blind zone may be smaller than the distance to the nearest city, giving meaningful warning time. The system works best for the scenarios where it matters least, and struggles most precisely in the scenarios where the stakes are highest. This is not a criticism of the people who built Shake Alert. They built an impressive system under real technical constraints. The blind zone is not an engineering failure, it is a physics constraint. But it is a constraint that receives far less public attention than the system's successes. And the blind zone is only the first layer of a blind spot that gets significantly larger when you zoom out from individual fault systems to the entire country. Part 4. The half of America with nothing. Open a map of Shake Alert coverage. The area covered is California, Oregon, and Washington. 3 states out of 50. The geographic strip running along the Pacific coast, representing roughly 10% of the continental United States by land area. Now open a map of seismic hazard across the United States. The highest hazard zones are, predictably, along the west coast. The Cascadia subduction zone, the San Andreas fault system, the active volcanic arc running through the Cascade Range. These are the areas Shake Alert covers, and the match between coverage and high hazard is intentional. But seismic hazard does not stop at the California-Nevada border or at the Cascade crest. It does not follow state lines or federal program boundaries. It follows geology. And American geology is not confined to the Pacific coastline. The New Madrid seismic zone, the Wasatch Front in Utah, the Charleston seismic zone in South Carolina, the Wabash Valley seismic zone spanning Illinois and Indiana, the Intermountain seismic belt running from Montana through Nevada. These are not theoretical hazard zones drawn on academic maps. They are geologically active fault systems with documented histories of significant earthquakes, some of the largest ever to occur on this continent, and none of them have early warning coverage. Not a single sensor in the Shake Alert network, not a single algorithm watching the ground, not a single government server ready to send an alert to the phones of the people who live above these fault systems. When the ground starts moving, how many seconds do you have? And does the system even know to start counting? For a resident of Memphis, Tennessee, the answer is 0. Not 0 seconds of warning, 0 infrastructure dedicated to providing any warning at all. The Memphis metropolitan area, home to more than 1 million people, sits directly above the New Madrid seismic zone, a fault system capable of producing magnitude 7 and magnitude 8 earthquakes that historical records show has done exactly that, multiple times. In the early 19th century, a sequence of New Madrid earthquakes so powerful that they rang church bells in Boston and caused the Mississippi River to flow briefly backward. Events of that scale today would affect a built environment that was not designed with significant seismic risk in mind, because the political and regulatory attention required to mandate seismic building codes follows the coverage of early warning systems, follows the funding for sensor networks, follows the prioritization of one geographic area over another. The half of America with no early warning system is not the half with no earthquakes. It is the half with no political leverage to demand the infrastructure that the other half takes for granted. Part 5. The New Madrid problem. The New Madrid seismic zone deserves its own section because its specific characteristics make the absence of early warning infrastructure not just an inconvenience, but a genuine compounding of a risk that is already poorly understood by the public, by local governments, and by the emergency management systems responsible for protecting the people who live above it. The seismic zone runs beneath parts of Missouri, Arkansas, Tennessee, Kentucky, and Illinois. It sits in the middle of the North American plate, far from any plate boundary, which makes it what seismologists call an intraplate fault system. Intraplate earthquakes are notoriously difficult to study and characterize because they do not occur on the well-defined plate margins where most seismological research is concentrated. The fault geometry is poorly constrained. The stress accumulation rate is slow and difficult to measure with surface GPS networks. The paleoseismic record, the geological evidence of past ruptures preserved in the sedimentary layers beneath the Mississippi River floodplain, is incomplete and actively debated. What is not debated is the potential magnitude. The 1,811 and 1,812 New Madrid earthquakes, estimated at magnitudes between 7 and 8, produced effects that were documented across an area larger than any earthquake in US history before or since. The shaking was felt from the Gulf Coast to Canada, from the Atlantic seaboard to the Rocky Mountains. The Mississippi River did things that observers at the time found difficult to put into words. Boats were capsized. Islands appeared and disappeared. The river flowed backward in localized sections as the riverbed was disrupted by the ground deformation. In 1811, the population living above the New Madrid seismic zone was sparse. Small frontier settlements, Native American communities, river traders. The built environment was almost entirely wood structures, with no basements, no foundations designed for lateral loading, no reinforced concrete. Today, the built environment above the New Madrid seismic zone is Memphis, Tennessee, St. Louis, Missouri, Paducah, Kentucky, Jonesboro, Arkansas. Hundreds of smaller cities and towns spread across a region where the soil is predominantly soft alluvial sediment deposited by the Mississippi and its tributaries over millennia. Soft sediment does something specific during earthquake, shaking that geotechnical engineers call amplification. It takes the seismic energy traveling upward from depth and makes it larger at the surface, not smaller. A magnitude 7 earthquake in soft river sediment does not produce the same shaking as a magnitude 7 earthquake in hard rock. It produces more, often significantly more. And the structures sitting on that amplified ground in the central United States were largely not built to handle it because the building codes in the region do not require the same seismic design standards as California, because the regulatory framework follows the perceived risk, and the perceived risk follows the public attention, and the public attention follows the coverage. When the ground starts moving, how many seconds do you have, and does the system even know to start counting? For the central United States, the answer to the second question is still no. There is ongoing research. There are academic proposals. There are USGS hazard maps that clearly show the seismic risk above the New Madrid zone, but there is no shake alert. There is no operational sensor network dedicated to early warning for the region's population. There are general-purpose seismic monitoring stations that contribute to the National Seismic Network, and that would detect a large New Madrid event within seconds of rupture. But detection and early warning are different things. The monitoring stations record what happens. An early warning system sends you a message before it happens to you. Those are functionally different products operating on different timelines and requiring different infrastructure and different funding and different political commitment. The New Madrid seismic zone is not waiting for that commitment before it considers its next rupture. Geology does not wait for budget cycles. Part 6. Why Cascadia could break the system. Back on the West Coast, inside Shake Alert's coverage area, there is a specific scenario that the system's designers have been grappling with since before the first sensor went into the ground. It is not a scenario they have solved, and it is the scenario with the highest potential consequence of any seismic event in the United States. The Cascadia Subduction Zone. A 1,000-kilometer fault system running offshore from northern California to the southern coast of British Columbia, where the Juan de Fuca plate is diving beneath the North American plate at roughly 3 to 4 centimeters per year. The last time the full Cascadia system ruptured, on the 26th of January 1700, it produced an earthquake, estimated at magnitude 9, sent a tsunami across the Pacific that struck the Japanese coast with enough force to be recorded in contemporaneous documents, and dropped the coastline of what is now the Pacific Northwest by as much as 2 meters in an instant. Shake Alert covers the coastline, the sensors are there, and for a full Cascadia rupture the system will fire, the alerts will go out. Here is the problem. The rupture of a full Cascadia megathrust would initiate offshore, roughly 50 to 100 kilometers from the coast, depending on which segment initiates first. The distance between the rupture and the coastal communities is not large, and the shaking from a magnitude 9 earthquake does not arrive gently. It arrives as sustained violent ground motion lasting 3 to 5 minutes, orders of magnitude longer than the brief sharp shaking most people in the Pacific Northwest have experienced from smaller crustal earthquakes. In the communities along the Oregon and Washington coast, the projected Shake Alert warning time for a full Cascadia rupture ranges from approximately 15 to 45 seconds in most scenarios. Some models suggest slightly more, some suggest slightly less. The specific warning time depends on where on the fault the rupture initiates, how fast it propagates, how quickly the sensors detect a confident magnitude estimate from a slow-developing megathrust rupture, and how quickly the alert travels through the wireless carrier network to individual phones. When the ground starts moving, how many seconds do you have? And does the system even know to start counting? 15 to 45 seconds. For a community that has been advised to get to high ground immediately after a major earthquake, because the first tsunami wave may arrive in 15 to 30 minutes in some coastal locations, 15 to 45 seconds of additional warning is meaningful. It is not nothing, but there is a specific problem with Cascadia that goes beyond the warning time. Megathrust earthquakes, specifically the kind generated by old cold oceanic plates subducting at shallow angles, do not always look like ordinary earthquakes in the first few seconds of rupture. They can begin slowly. The initial rupture nucleates on a small patch of the interface and then grows as stress cascades to neighbouring patches. In the early seconds of a megathrust rupture, before the full magnitude is apparent from the seismic waveforms, the system's magnitude estimate is uncertain. It may underestimate the eventual size. And an underestimate means the projected shaking zones in the alert may be smaller than what the earthquake will actually produce. For a slow-developing magnitude 9 megathrust, Shake Alert may initially estimate a magnitude 7.5 or 8 before the full extent of the rupture becomes apparent in the data. That means the first alert might underestimate the shaking for inland communities. It might fail to issue an alert to communities that will ultimately experience damaging shaking because the initial estimate suggests those communities are outside the projected damage zone. This is a known technical challenge. It is actively researched. Algorithms have been developed to try to address the slow rupture problem. None of them has been tested against an actual full-margin Cascadia rupture because no full-margin Cascadia rupture has occurred since Shake Alert or any comparable modern monitoring system existed. The testing is necessarily theoretical, done on synthetic seismograms and historical records from other megathrust events, like the 2011 Tohoku earthquake in Japan. The system is doing its best. The people building and running it are doing their best. But the scenario it was specifically built for, the Cascadia megathrust, is also the scenario where the system's known technical limitations are most consequential. Part 7. The Warning Time Math. Let me be precise about something that gets lost in almost every public discussion of earthquake early warning. Because the way warning times are talked about in official communications and in press coverage creates a systematic misunderstanding of what the system can and cannot do. And that misunderstanding has real consequences for how people think about their own safety. Warning time. In the context of earthquake, early warning is not a single number. It is not a promise. It is a range that varies based on 4 factors that interact in ways that are not intuitive. The distance from your location to the earthquake's epicenter, the depth of the earthquake's hypocenter, the density and proximity of the sensor network to the rupture, and the time required for the alert to travel from USGS servers through wireless carrier infrastructure to your specific device. A person in San Francisco receives a different warning time for a magnitude 6.5 on the Hayward Fault than a person in Oakland for the same event. Not because San Francisco is less important, but because the geometry of the fault and their respective distances from the epicenter are different. Let me give you the math in plain terms, because plain terms are what matter here. The S-wave from an earthquake travels at roughly 3.5 kilometers per second. If you are 35 kilometers from an earthquake's epicenter, the S-wave takes 10 seconds to reach you. If the Shake Alert system can detect the earthquake and send the alert to your phone in 5 seconds, you have 5 seconds of warning before the shaking begins. If you are 7 kilometers from an epicenter, the S-wave takes 2 seconds to reach you. Even if Shake Alert processes the alert in 3 seconds, you receive the alert 1 second after the shaking has already started. Negative warning. The system sent the alert is correct. You are already shaking by the time it arrives. This is not a hypothetical. This is the expected performance of the system in dense urban areas, situated close to major fault lines. The people who live closest to the faults, the people who will experience the most intense shaking, are the people who receive the shortest warning times or no warning time at all. When the ground starts moving, how many seconds do you have? And does the system even know to start counting? There is a documented benefit even to very short warning times. Research on Shake Alert's performance during the earthquakes has successfully warned against SHO's measurable behavioral responses. People instinctively brace. They move away from windows. They stop vehicles. The alert triggers a physiological response even when the cognitive process of deciding what to do has barely begun. This is not trivial. The difference between being braced and unbraced when shaking begins can determine whether a falling object injures someone. But 10 seconds is enough to duck under a desk. It is not enough to evacuate a building. It is not enough to get to a tsunami evacuation zone. It is not enough to do most of the things that emergency preparedness messaging tells people to do when an earthquake strikes. Because most of that preparedness messaging was written assuming more warning time than the system can actually deliver for the scenarios closest to fault lines where damage is most severe. The honest summary of the warning time math is this. If you live far from a major fault and a moderate earthquake occurs nearby, Shake Alert could give you 30 seconds, a minute, possibly more. That is genuinely useful time. If you live directly above a major fault capable of producing a damaging earthquake, the system may give you 5 seconds, or 2 seconds, or nothing at all. And the places where you live directly above major faults are Los Angeles, Seattle, Portland, the communities along the Cascadia coast, and dozens of smaller cities and towns where the fault runs beneath the neighborhood, not beside it. Part 8. The sensor gap nobody talks about. Shake Alert's blind spot is not just geographic. Even within the 3-state coverage area, the sensor network is not uniformly dense, and sensor density is not a minor technical detail. It is the foundational variable that determines how quickly the system can make a confident determination about an earthquake's location, magnitude, and likely shaking zone. More sensors mean faster, more accurate alerts. Fewer sensors mean slower processing, less certainty, and higher probability that the alert will be imprecise or delayed. The USGS has published sensor density targets that specify how many seismic stations per unit area are needed to achieve the warning times that make the system practically useful. In the most seismically active and most densely populated areas of California, those density targets have been partially met. In rural areas of Oregon and Washington, in the offshore regions above the Cascadia interface, and in transition zones between dense urban clusters and less populated terrain, the sensor networks are thinner than the target specifications require. This matters because of how the algorithm works. Shake Alert needs data from multiple sensors to triangulate an earthquake's location and confirm its magnitude. The more sensors reporting, the faster that triangulation is completed and the more confident the magnitude estimate becomes. An earthquake detected by 10 nearby sensors produces a more rapid and more accurate alert than the same earthquake detected by 3 sensors at greater distance. In the offshore zone above the Cascadia Fault, where an initiating megathrust rupture would generate the first seismic signals, sensor coverage is necessarily limited. Seismometers on the seafloor are expensive, difficult to install, harder to maintain, and require specialized data transmission infrastructure. The offshore sensor network that USGS and partner institutions have worked to build is real and growing, but it remains less dense than the land-based network, which means that for the initiating rupture of a Cascadia megathrust, the system is reading the first signals through a sparser network than it would face for an onshore event of comparable magnitude. When the ground starts moving, how many seconds do you have, and does the system even know to start counting? The sensor gap is a funding problem as much as it is an engineering problem. Seismometers cost money, installation costs money, maintenance costs money, data transmission infrastructure costs money. The ongoing operational budget of Shake Alert, covering station maintenance, data center operations, algorithm development, and the staff who run all of it, is funded through a combination of USGS appropriations and state contributions that has consistently fallen below the levels seismologists have identified as necessary for the system to perform at its design specifications. Every year that a sensor goes unmaintained and fails, the network gets slightly thinner. Every year that a planned new station does not receive funding, the coverage gap persists. The blind spot has a budget number attached to it, and the budget has not been sufficient. Part 9. Japan did this decades ago. There is a country that solved the earthquake early warning problem. Not perfectly, not without limitation, but substantially and comprehensively, in a way that the United States has not come close to matching. And the comparison is worth making in detail because it is instructive not just about the technology, but about the choices that determine whether a country builds infrastructure proportional to its actual seismic risk. Japan deployed a national earthquake early warning system in 2007. 18 years before this script was written, Japan had an operational system covering the entire country, not 3 prefectures, not the most seismically active coastal strip, the entire country. Japan's system, operated by the Japan Meteorological Agency, uses a network of more than 4,000 seismic observation points distributed across the Japanese islands. For comparison, Shake Alert, covering 3 US states with a combined land area nearly twice that of Japan, uses approximately 1,700 stations. Japan has more than twice the sensor density covering a smaller geographic area. And Japan's system was built to those specifications not in response to a funding crisis or a political compromise, but because the Japanese government made a national policy decision that earthquake early warning infrastructure was essential public safety infrastructure that warranted investment comparable to other emergency systems. When the ground starts moving, how many seconds do you have, and does the system even know to start counting? Japan's system has been tested against real large earthquakes in ways that Shake Alert has not. The 2011 Tohoku earthquake, magnitude 9, the most powerful earthquake ever recorded in Japan, triggered warnings across the country before the most intense shaking arrived in inland areas. The system performed not perfectly. The areas closest to the offshore rupture, the same blind zone problem that Shake Alert faces, received little or no warning. But for much of the country, the alerts worked. Trains stopped. Automated safety systems activated. Industrial processes were interrupted before the shaking arrived. The comparison between Japan's system and America's is not a comparison between 2 countries with equal seismic risk, where one simply made a better technical decision. Japan faces arguably greater seismic risk than the United States because of the complexity and frequency of its subduction zone activity. But Japan also made the policy decision, decades ago, to invest in national earthquake monitoring infrastructure as a core function of government rather than as a discretionary program funded year to year through congressional appropriations processes. The United States has not made that decision. Shake Alert exists because specific advocates within the USGS, within universities, within state governments, fought for specific funding allocations over many years. It is a scientific and engineering achievement built against the resistance of a funding environment that treats earthquake early warning as a regional specialty program, rather than as national infrastructure. And the result is a system that covers 3 states, has sensor density gaps within those states, and leaves the majority of the country's seismically active regions without any operational warning capability. Part 10. The Induced Seismicity Blind Spot. The earthquake threat in the central United States is not only geological and historical, it is also ongoing and in significant part human-made. The dramatic increase in earthquake frequency across Oklahoma, Kansas, Arkansas, and parts of Texas that began around 2009 and peaked around 2015 is one of the most thoroughly documented geophysical phenomena associated with industrial activity in the last century. In 2009, Oklahoma experienced roughly 1 magnitude 3 or greater earthquake per year. By 2015, that number had risen to more than 900. The cause has been established by multiple independent research teams and is not seriously disputed in the scientific literature. The injection of large volumes of wastewater, a byproduct of oil and gas production including hydraulic fracturing operations, into deep disposal wells has been reactivating ancient fault systems in the Oklahoma basement rock, systems that were geologically stable for millions of years until the pore pressure changes associated with massive fluid injection brought them closer to failure. Oklahoma, during the peak years of induced seismicity, briefly surpassed California as the state with the most earthquakes in the continental United States. That is not a geological coincidence. That is an industrial consequence, and it is a consequence that occurred, and continues to occur in reduced but not eliminated form, in states with no earthquake early warning infrastructure. When the ground starts moving, how many seconds do you have, and does the system even know to start counting? The induced seismicity problem compounds the blind spot in a specific way. Induced earthquakes tend to occur near active injection wells, which are distributed across the landscape of Oklahoma and surrounding states in patterns determined by the location of the oil and gas reservoirs being exploited. These locations are not always near population centers, but they are also not always far from them, and the fault systems being reactivated by injection are not always small. Oklahoma has experienced induced earthquakes reaching magnitude 5.8, an event that caused structural damage in Pawnee, Oklahoma, in 2016, the largest earthquake in the state's recorded history, and an event driven in significant part by wastewater disposal. If a magnitude 5.8 induced earthquake occurred near a major US city in the central United States today, there would be no early warning. There would be no alert. The first signal to most residents would be the shaking itself, which is the same situation that would exist for a naturally occurring New Madrid earthquake, or a Charleston earthquake, or an earthquake on any of the active fault systems across the 2/3 of the country that Shake Alert does not reach. The human-made seismicity problem is being reduced. Regulatory action in Oklahoma has led to reductions in injection volumes and a measurable decrease in earthquake frequency since the 2015 peak. The science connecting injection and seismicity has been used to implement buffer zones and injection protocols designed to reduce the risk of fault activation. But the underlying fault systems that were reactivated remain in a different stress state than they were before injection began. The fluid pressure changes propagate slowly through the rock long after injection stops. Reactivated faults do not simply return to their pre-industrial baseline when the injection wells are shut down. The seismicity decays, but the system has been altered. And the altered system continues to produce earthquakes in states that have no early warning infrastructure and, in many cases, no building codes designed for the seismic loading that a significant earthquake would produce. Part 11. The alert that never reaches your phone. Let us assume for a moment that you live inside Shake Alert's coverage area, that you live in California, Oregon, or Washington, that the sensors above your local fault system are well maintained and densely deployed, that when an earthquake ruptures nearby, the Shake Alert algorithm fires correctly and issues an accurate alert within 5 seconds of rupture initiation. That alert still has to get to your phone, and the pathway between the USGS server and your pocket involves infrastructure that is not under the USGS's control and that does not always perform the way earthquake early warning systems require. Shake Alert alerts are delivered to the public primarily through wireless emergency alerts, the same system that sends you Amber Alerts, presidential alerts, and severe weather warnings. The WEA system is a cell broadcast technology. Unlike a text message, which travels through the carrier network to a specific subscriber's device, a WEA message is broadcast from all cell towers in a geographic area simultaneously. Any phone within range of those towers that is configured to receive emergency alerts will display the message regardless of whether the user has installed a specific app. This is the right architecture for earthquake early warning. Cell broadcast is fast. It does not depend on routing individual messages to individual subscribers. The tower broadcasts and every compatible device in range receives simultaneously. But the system has documented weaknesses that the earthquake early warning context makes critical. When the ground starts moving, how many seconds do you have? And does the system even know to start counting? Some phones receive WEA alerts faster than others depending on the manufacturer, the carrier, and the specific implementation of the cell broadcast protocol on the device. Research on Shake Alert alert delivery during real earthquake events has documented variations in delivery time across devices in the same location ranging from less than a second to more than 5 seconds. In a context where the total warning time might be 8 seconds, a 5-second variation in alert delivery is not a rounding error. It is the entire warning window. The phone must also be powered on, not in airplane mode, and connected to a cellular network. In a situation where a person is in a building with poor cellular penetration, in an underground parking structure, in certain types of reinforced concrete construction that attenuate cell signals, the alert may arrive late or not at all. There is a Shake Alert compatible app, MyShake, developed by researchers at UC Berkeley that supplements the WEA system and can deliver alerts through internet connections rather than cellular broadcast in some configurations. But app adoption, requires people to download and configure it, which requires awareness that the app exists, which requires public education campaigns that have not been funded at the scale required to reach most of the population that would benefit from them. A system that sends an accurate alert that does not reach the person who needs it has not warned anyone. The last mile of earthquake early warning, the path from the server to the phone, is not a solved problem. It is an operational challenge that varies by device, carrier, location, and a dozen other factors that no government agency fully controls. Part 12. The budget that was never enough. The Shake Alert system was formally authorized by Congress in 2016 through the Earthquake Hazards Reduction Act. The authorization established the legal framework for building and operating the system. What it did not establish was mandatory, sustained funding at the level that the USGS and its partner institutions identified as necessary to build the system to its design specifications. The difference between authorizing a program and funding a program is one of the most consequential gaps in American infrastructure policy. A program can be authorized for years while receiving annual appropriations that are a fraction of what the design specification requires, forcing the managing agency to make decisions about what to build, what to delay, and what to leave on the drawing board. Shake Alert has operated in exactly this gap. The total estimated cost to build the system to the sensor density and coverage specifications needed for it to perform as advertised across the 3-state coverage area has been estimated by USGS and partner institutions at several $100 million in initial capital investment, with ongoing operational costs of tens of millions per year. Annual appropriations for Shake Alert have fluctuated and have not consistently reached those levels. The result has been a system that is real, operational, and genuinely valuable, but thinner than its design is intended, and covering less ground than its advocates proposed. When the ground starts moving, how many seconds do you have? And does the system even know to start counting? The political economy of earthquake, early warning investment, follows a pattern that emergency management professionals recognize across many hazard types. Investment in hazard mitigation infrastructure is politically difficult because the benefit is invisible when the system works and catastrophic in retrospect when it does not. A senator does not win votes by explaining to constituents that they were not harmed by an earthquake that the monitoring network helped warn them about. They win votes by responding to visible crises, funding visible recovery operations, cutting ribbons on visible new infrastructure. The investment required to build an earthquake early warning system to full specification does not produce visible results on a political timeline that matches an election cycle. The earthquake it is designed for has not happened yet. The warning it would provide has not been delivered yet. The lives it might save exist only in probability distributions calculated by seismologists, whose language does not translate easily into the language of appropriations committees. This is not unique to earthquake early warning. It is the fundamental challenge of all investment in pre-event mitigation for low-frequency, high-consequence hazards. The return on investment only becomes visible after the event it was designed to prevent or mitigate, at which point the conversation shifts to why the investment was not made sooner rather than why it was made at all. The budget is not enough. The coverage is not complete. The sensor density is below specification in multiple regions. These are not secrets. They are documented in USGS reports, in academic literature, in the public statements of the scientists who operate the system. They are just not what gets communicated when the system successfully warns people in the Bay Area about a magnitude 4.7 aftershock. Part 13. The slow earthquake problem. Shake Alert was designed primarily for a specific category of earthquake. Fast rupturing fault systems where the energy releases suddenly, the P wave is sharp and impulsive, the magnitude estimate is rapid and confident, and the shaking arrives as a clear seismic event that the algorithm can process and characterize before the S-wave reaches populated areas. That is a good description of many earthquakes in California. Strike-slip faults like the San Andreas fail in relatively rapid, geometrically clean ruptures that produce the kind of seismic signals Shake Alert's algorithms were built to process. The system handles these events well. It handles a different class of earthquake significantly less well, and that class of earthquake is associated with the scenario most people in the Pacific Northwest have been told to worry about. Subduction zone megathrust earthquakes sometimes rupture slowly, not in the sense of creep or slow slip, but in the sense that the rupture velocity, the speed at which the break propagates along the fault interface, is lower than for typical crustal earthquakes of comparable magnitude. These events are sometimes described in the literature as tsunami earthquakes, a term coined by the seismologist Hiroo Kanamori to describe events that generate tsunamis larger than their body wave magnitude would predict. The physical reason for this is the specific geometry and material properties of the shallow subduction interface. The up-dip portion of the fault, the section closest to the seafloor and therefore most relevant to tsunami generation, is composed of mechanically weak sedimentary material. It fails differently on stronger, more brittle rock at greater depths. It ruptures slowly. The seismic waves it generates are lower frequency and longer period than the sharp P waves that Shake Alert's algorithms are most sensitive to. When the ground starts moving, how many seconds do you have? And does the system even know to start counting? For a slow-developing megathrust rupture, the early P-wave signal is weaker and more ambiguous than the system's detection algorithms expect. The magnitude estimate in the first 5 to 10 seconds may be substantially lower than the event's eventual magnitude as the rupture propagates and accumulates energy over a longer period. An event that eventually reaches magnitude 9 may look like a magnitude 7.5 inches the first 8 seconds of available data. The consequence is not that Shake Alert fails to issue any alert. It would issue an alert based on its best initial estimate, but the alert might underestimate the shaking for communities farther from the epicenter. It might not extend the warning zone as far inland as the earthquake's eventual magnitude would require. Communities that will experience damaging shaking might receive a reduced intensity alert, or no alert at all, because the initial magnitude estimate placed them outside the projected damage zone. This is the specific technical scenario that seismologists working on Shake Alert have been most concerned about and have devoted the most algorithm development effort to addressing. Real-time source characterization methods designed to detect the early signatures of megathrust ruptures before the full magnitude is apparent are being incorporated into the system. Progress is real, but the Cascadia megathrust has not produced a qualifying event since these algorithms were implemented. The testing against real Cascadia data has not happened because Cascadia has not ruptured. The system will face its most consequential test against the scenario it has never actually processed. Part 14. What the science says versus what the system does. Here is the tension at the center of Shake Alert's public communication challenge. The science behind earthquake early warning is strong. The physics is well understood. The benefits are documented from systems in Japan, Mexico, and Taiwan that have been operational through significant earthquakes. The value of even 5 seconds of warning is supported by research. The cost-benefit case for investment in early warning infrastructure, accounting for projected lives saved, injuries prevented, and economic losses reduced, closes at funding levels well above what the system currently receives. And the system as it exists today genuinely works. For the earthquakes it has warned against within its coverage area, it has performed within its design parameters. People have felt their phones buzz and have had seconds to brace themselves before shaking that would otherwise have arrived without any notice. That is real. That has value. But the gap between what the science supports and what the system delivers is not small. It is the gap between a sensor network built to specification and a sensor network built to budget. Between a coverage area that matches seismic hazard geography and a coverage area that matches the states that secured appropriations. Between an alert delivery system optimized for worst-case scenarios and one optimized for typical scenarios with worst-case performance left as a known limitation. When the ground starts moving, how many seconds do you have? And does the system even know to start counting? I want to be precise here because this section of tonight's discussion is the one most likely to be misunderstood. I am not saying Shake Alert does not work. I am saying Shake Alert works within constraints that most of the people who depend on it do not know about. The public communication around the system tends toward what it can do in favourable scenarios. It underemphasises what it cannot do in the scenarios that involve the most people in the most danger. This is not a criticism of the scientists who built and operate the system. They are clear about the system's limitations in technical literature, in internal reports, in academic conference presentations. The information exists. It is just not what gets amplified when the system successfully warns a city about a moderate earthquake, and the alert is celebrated as proof that the system is ready for the big one. Being ready for a magnitude 5.5 inches, a well-instrumented region, and being ready for a full Cascadia megathrust are not the same state of readiness. And treating them as equivalent in public communication is a disservice to the populations who will have to make real decisions in real time based on what they believe the system can deliver. Part 15. Conspiracies versus the real failure. Number. When earthquake early warning coverage gaps are discussed online, a specific type of explanation tends to fill the information vacuum. If the government has not built a warning system for the central US, there must be a reason beyond funding and political prioritization. The reason offered is usually that they do not want people to know what is coming. That information about impending earthquakes is being suppressed to prevent panic. That the USGS has data it is not releasing, because releasing it would cause an uncontrollable public response. I want to address this directly because the people who encounter these claims deserve an honest response, not a dismissal, and not a validation, but an honest engagement with what the evidence actually shows. The USGS publishes its seismic monitoring data in real time. All of it, every earthquake, detected by the National Seismic Network above the detection threshold, appears in public databases within minutes of its occurrence. The USGS Earthquake Hazards Program website is one of the most comprehensively public government data portals that exists. You can access current and historical seismic data, hazard maps, fault databases, and technical reports at any time. None of this data is classified. None of it is withheld. The agency operating the monitoring system operates it transparently. If earthquake prediction were possible with any reliability, the USGS would not suppress it. This is important to understand not as a defense of institutional good faith, but as a statement of institutional self-interest. An agency that predicted a major earthquake and issued a warning that saved thousands of lives would receive more funding, more political support, and more institutional credibility than any other outcome it could achieve. The incentive structure runs entirely against suppression. Earthquake prediction is not currently possible with operational reliability. This is not because the relevant information is being hidden. It is because the physical system that generates earthquakes does not produce signals that our instruments can reliably interpret as precursors at the timescales and specificities that would constitute useful prediction. The fault accumulates strain invisibly. The failure threshold is not directly measurable. The transition from locked to catastrophically sliding happens at scales and depths that our instruments cannot directly sample. When the ground starts moving, how many seconds do you have? And does the system even know to start counting? The real failure is not concealment. It is mundane. It is the consistent underfunding of infrastructure that seismologists have clearly described as necessary, and that policymakers have consistently judged as lower priority than other budget items. It is the geographic inequity that concentrates early warning coverage in 3 states while leaving the rest of the country's seismically active regions without any operational system. It is the political economy of disaster preparedness investment that makes pre-event mitigation perpetually difficult to fund against the competing demands of an annual appropriations process. These failures are not hidden. They are documented in public USGS reports, in Government Accountability Office, analyses of Shake Alert's funding history, in the congressional testimony of scientists who have repeatedly told appropriations committees that the system needs more investment and received responses that produced inadequate appropriations. The information is available to anyone who reads it. The failure is not in the concealment of data, it is in the political decisions about what to invest in. The conspiracy narrative replaces a complicated and genuinely frustrating story about institutional priorities and political inertia with a simpler story about malicious intent. The simpler story is more emotionally satisfying but less accurate. And less accurate narratives lead people to demand things that would not actually address the problem, while the actual problems go unaddressed because the conversation has moved to a framework that does not match the evidence. Part 16. The political blind spot. The geographic blind spot in Shake Alert's coverage is not arbitrary. It follows a specific pattern that is worth naming clearly. The states with full Shake Alert coverage are California, Oregon, and Washington. These are democratic-leaning states with active scientific communities, strong university seismology programs, significant political representation in Congress, and histories of using seismic events to drive public policy investment in preparedness infrastructure. The 1989 Loma Prieta earthquake in the San Francisco Bay Area, the 1994 Northridge earthquake in Los Angeles, the ongoing awareness of Cascadia subduction zone risk in the Pacific Northwest. All of these have produced political constituencies and organizational infrastructure that have sustained the advocacy necessary to secure federal funding for seismic monitoring. The states without shake alert coverage include Missouri, Tennessee, Arkansas, Kentucky, Illinois, South Carolina, Utah, and the rest of the seismically active but politically differently situated regions of the country. Some of these states have historically prioritized other concerns in their federal legislative agenda. Some have received less consistent advocacy from the scientific community on this specific issue. Some have building code and preparedness infrastructure that reflects the lower perceived priority given to earthquake risk relative to other hazards, more consistent with their historical experience. When the ground starts moving, how many seconds do you have? And does the system even know to start counting? The result is not that the government decided California's population matters more than Missouri's. It is that the political process produced funding allocations that have systematically prioritized the regions where the advocacy was stronger. This is how most federal infrastructure investment decisions are made. They reflect the political capacity of the affected regions to sustain organized advocacy over the years required to move from an authorized program to an adequately funded one. Memphis is not less deserving of earthquake early warning infrastructure than Los Angeles. The New Madrid seismic zone is not less dangerous than the southern San Andreas. The absence of a shake alert sensor network in the central United States is not a reflection of an objective risk assessment that concluded the hazard was insufficient to justify investment. It is a reflection of a political process that does not yet produce the advocacy, the appropriations, and the sustained commitment necessary to build the system that seismologists have clearly described as warranted. That distinction matters because it points toward the remedy. The blind spot in America's earthquake early warning system is not a technical limitation without solution. It is a political and funding failure with a known resolution that requires political will that has not yet materialized in the states and regions most affected. Part 17. The seconds that define everything. Let me close the technical discussion with something specific. Something that makes the abstract warning time calculations concrete in the way that abstract calculations rarely manage to be. On the 18th of April 1906, a magnitude 7.9 earthquake ruptured the northern San Andreas Fault and virtually destroyed San Francisco. The city burned for 3 days after the earthquake, the fires ignited by ruptured gas lines and fueled by water mains broken by the shaking. More than 3,000 people died. Hundreds of thousands were displaced. An estimated 80% of the city was destroyed. There was no early warning. There was only the earthquake itself, arriving at 5:12 inches the morning when most of the city was asleep, preceded by nothing, announced by nothing, leaving approximately 47 seconds of violent shaking as the only information the population received that something had happened. A shake alert system operating in 1906 San Francisco, with the sensor density that exists today in the Bay Area, would have issued an alert to residents of San Francisco approximately 15 seconds before the S-wave arrived from the northern San Andreas rupture. Not 15 minutes. 15 seconds. When the ground starts moving, how many seconds do you have? And does the system even know to start counting? 15 seconds is not enough to evacuate a building. It is enough to wake up, to orient yourself to what is happening before the shaking starts, rather than in the disorienting first moments of the shaking itself. It is enough for automated systems to shut off gas lines, which would have materially reduced the fires that killed more people in 1906 than the earthquake itself did. It is enough for hospitals to secure patients and for power plants to initiate protective shutdowns. It is enough for the information that something is happening to precede the violence of the shaking itself by an interval that changes how people respond. 15 seconds is not nothing. 15 seconds, multiplied across millions of people, and billions of dollars of automated safety systems that can be triggered by an early warning alert, is a meaningful reduction in the consequences of an event that will happen again regardless of whether there is a warning system in place. The earthquake happens. That part is physics. The only variable is how prepared the population and infrastructure are when it arrives, and preparation requires warning. Warning requires infrastructure. Infrastructure requires funding. Funding requires political commitment. And political commitment requires the public to understand that the system that is supposed to warn them has a blind spot large enough to encompass most of the country they live in. Part 18. Final synthesis. Let me build the full picture one last time because you deserve to hold all of it at once. America has an earthquake early warning system. It is called Shake Alert. It is real, operational, and genuinely valuable within its coverage area. It represents a scientific and engineering achievement that took decades of advocacy and work to bring to operational status. It covers 3 states, California, Oregon, Washington, out of 50. It has a blind zone within those 3 states, where the physics of seismic wave propagation means that the alert and the shaking arrive simultaneously or in reverse order for communities closest to the fault. It faces a specific technical challenge in detecting slow-developing megathrust earthquakes of the type that the Cascadia subduction zone, its most consequential scenario, would produce. It depends for its last mile on wireless carrier infrastructure that delivers alerts with variability that can consume the entire warning window. It is funded below the levels that its operators have identified as necessary to perform at its design specifications. The 47 other states have nothing. The New Madrid seismic zone, capable of producing an earthquake felt from Canada to the Gulf of Mexico, has no sensor network dedicated to early warning. The Wasatch Front in Utah has no coverage. The Charleston seismic zone has no coverage. Oklahoma, where industrial activity has dramatically elevated earthquake frequency over the past decade, has no coverage. The East Coast has no coverage. When the ground starts moving, how many seconds do you have? And does the system even know to start counting? This is the honest state of earthquake early warning in the United States today. Not a crisis, not a secret, not a conspiracy, but a documented gap between the seismic risk that geology and human activity have created and the infrastructure that political will and funding have produced to address it. The system cannot see what it was not built to see. The warning cannot come from infrastructure that does not exist. And the infrastructure that does not exist is not absent, because the risk is not real. It is absent because the real risk has not consistently produced the political attention required to fund the solution that seismologists have clearly described. The next great earthquake in the United States will happen when the physics requires it to happen. Not when the political calendar permits it. Not when the appropriations process has been satisfied. Not when the sensor network has reached the density that seismologists have been requesting for years. The fault does not wait for the budget to catch up to the hazard. When it happens, the question of how many seconds of warning the population received will be answered definitively, and in the aftermath, the documented history of underfunding, coverage gaps, and known blind spots will be read by people trying to understand why the system that was supposed to protect them did not fully deliver on what they had been told to expect. The blind spot is not a mystery, it is a choice, and choices, unlike earthquakes, can be reversed before the shaking starts. The question is whether they will be.